Alright, so basically a slump test would look like um, this. You have a conical mold, so it has a prescribed dimension, so it has a standard dimensions, where you pour your concrete mix. So it's just a sample, and then after that you invert this mold, and then place the mix on a flat surface, and then try to remove this mold. Okay, so let's say we have this, it's already filled with mix. So once we try to remove the mold, then what will happen to the slump? So if the slump uh, remains the same, I mean uh, did not decrease in height, then that's gonna be what we call as true. Oh no, that's not true. That's a zero slump. Okay, so probably you get less water. Um, so that's not what we wanted. So another response would be something like, instead of um, another response would be there's gonna be a decrease in height. So if there's a decrease in height, that's what we call a true slump. Okay, and then another one would be, for example, this is your mold, and what happened is it pure collapse. Then that just means that you have too much water. And if you have, um, let's say, a portion only collapse, so that's what we call a shear slump. Okay, so meaning probably that's not it's not mixed properly, or probably not mixed well. Okay, so a detailed discussion about the slump test can be found in our lecture handouts. Um, Next, we'll move on to the topic on mixing proportions. So recall that a concrete is actually comprises of different materials such as cement, sand, and gravel. So the proportions of these ingredients would also affect the strength of the concrete. Okay, so let's write down the ingredients. So we have cement, sand, and gravel. Okay, so if there's gonna be a proportion like 1:2:3, so meaning one portion of cement, then you include two portions of sand, and then two portions of gravel, then that mix would have a corresponding strength. Okay, and that mix 1:2. Oh, sorry, that's not three. There's supposed to be four. Okay, so if this mixing proportion is what we call as class A, right? So class A. So if we have 1:2.5 is to 5, so you notice just times 2, so 2.5 times 2, that's 5. Then that's gonna be class B, and class C, 1:3:6. And there's also um, data on this class double A. We have 1:1.5 times 3. Okay, so you notice that um, for this given volume, right? So in this given volume, there's lot, or let's say there's more percentage of cement. So meaning more cement in that given mix. So if you get more cement, then there's gonna be uh, high strength, right? So high strength, and then sorry, the bottom would be low strength. Okay, so the reason why there's these different class proportions is simply because the different applications, for applications that requires much strength, then you would need this probably double A or A, class A proportions, for example beams and columns. Okay, but for structural members that does not much require strength, then probably you can use a class, let's say class B or class C, depends upon the designer and the applications. Okay, so the point here is, of course, for class C, you get um, you get a volume with lesser amount of cement. So meaning that you have lesser cement bags in a given, let's say, in a given mix. So that would be, let's say, lesser amount of cement bags. That meaning lesser cost. So you can equate that cost. So if you have this class double A, then you get more cement on a given mix. Then meaning you get more cement bags. So more cement is just more cost. All right. So the details you can read that in our lecture handouts. Now let's move on to the properties of concrete. So concrete has a lot of properties, and you can find that or you can read that in many reinforced concrete textbooks, or textbooks regarding reinforced concrete designs and stuff like that. But for us here, I'd like to only point out one property, and that's the compressive strength. Okay, because most of our equation gonna be depend going is going to depend on this compressive strength. Okay, of course, other properties may also appear in some calculations, but mostly it's just the compressive strength. Okay, so how is the compressive strength of concrete is determined? So there is a sample, right? There is a specimen of concrete specimen, this cylindrical shape, and the height is 300 mm, or you can convert that in English units. And this is 150 mm, so this is 6 inches by 12. So you take the sample in a universal testing machine, right? Right. So let's say this is the universal testing machine. So it can test the compressive strength, tensile, or whatever. Okay. So there is, let's say there is a something like a part here, a portion here that it presses down this test specimen. So you put this cylindrical specimen here, and then you apply the loads. So the loads, let's say once applied, then it records what's going to be the strain, the stress strain, let's say compressive strength over the strain. Okay, so it was found out that for lower grade of concrete, there's a the behavior is something like this. Then for higher grades of concrete, then something like this probably, and then probably like this for a much higher grades. So you notice that this is a stress strain curve, right? So you notice that for lower grades of concrete, you get a more ductile, right? You get a more, you can strain more, whereas for for higher grades, you can only strain less. That's gonna be fractures. Of course, you get high compressive strength, but you get the ductility or the brittleness is affected. Okay, so the compressive strength of concrete is written in the symbol of FC prime. So the unit is megapascals. Okay, so that's megapascals. So I think you just have to get used to these notations that stresses, but it's written in this symbol FC prime. Unlike in our strength of material course, where we use the stress something like this, the sigma. Okay, so going back to this curve, you notice that there's gonna be some value that no matter or what type of of grades of concretes that you use, you're gonna fail in a strain value of um, 0. Okay, that's 0.002. Okay, so typical strength that we'll encounter in the calculation would be something like 21 megapascals or to 30 plus or something megapascals. So compare that to the strength of steel. Steel is around, let's say, 250 megapascals to something like 400 plus or something. So it's just I think there's just 10% or around or roughly 10% of the strength of steel. But for this is compressive. For steel, that's 200. I mean, that's this is tensile strength. Although there are literatures that for ductile materials, it's almost the same or near each other for the compressive and tensile strength. Okay, so now let's go to the reinforcing steel. So reinforcing steel. Okay, so there are two types. We have a deformed bars, and we also have welded wire fabric. Welded wire fabric. Okay, so deformed bars are the typical bars that you see. Just something like, for example, 16 mm or 12 mm in diameter with these lugs on its surface. And for this welded wire, it's actually a wire mesh. So it's a solid bars, probably let's say 1/8 inch or 3 mm inch. 3 mm inch. Sorry, I mean 3 mm. What do they call that? 3 mm in diameter, not 3 mm inch. Right. So just sorry um, for the nonsense. All right. So it's something like this. You can buy that in, let's say, 4 by 8. So that's 4 feet by 8 feet. So this is, let's say, 4 inches. Then this one is 8 inches. 8 inches. Sorry. Uh, I mean 8 feet. So 4 feet by 8 feet. And this one, the bores, the diameter is probably 3 mm, and then the spacing of the bores, that can be something like 2 inches. Okay, so that's a wire mesh. Whereas for this one, where you buy this in terms of length, so probably 6 meters, probably most common 60. I mean, is 6 meters, but other lengths may be available. Okay, so these are the two reinforcements that we provide in a concrete. So for beams, if you notice in a beam cross section, you get what you get a something like a rebars here, and then the stirrups. Then they're made up of deformed bars. For planar members, let's say walls or probably slabs, then this one can be used. But in our course, we'll only focus on this type of reinforcing steel. Okay, so the deformed bars, or rebars, or reinforcement bars. Okay, so for rebars, we have bar designations. So we have 10, 12, 16, 20, and 25. Although higher sizes, higher designations are also available, but probably we'll just limit our discussions to here. So take note that our bar designation is, I think this is in the PNS or Philippine National Standards. There's also other bar designations. I don't know if it's in ASTM or something, but they have like number three bars, or uh, s- I don't know, probably number 8 or something like that. But there is a corresponding, or there's an equivalent bar diameters. But this one is just in at least it is in we can visualize that it's in mm, right? So there's 10 mm, 12, 16 mm. And then there are data for the nominal area in our lecture handouts plus the nominal mass. Okay, so just basically pi d squared over 4 or something. Okay, more or less. Now when I say nominal area, from the word nominal, it's just something like a specification, although it may not be necessarily that's exactly let's say 79 mm squared. So it's something like a way of specifying a rebar. Okay, so you'd also notice that there's going to be markings in the rebars. And now let's go to the properties, right? So properties of reinforcing steel. So we also discussed earlier the properties of concrete, and now we'll discuss the properties of reinforcing steel. So goes true with the same goes true with steel and how you determine the strength of the steel. So again, just need to go to the universal testing machine or testing machine. Okay, because when you say universal, it just means that you can do probably many types of testing. The point here that's gonna be in tensile test. So you have your something like a jaw or a grip or something, and then you have your rebar. So this rebar, you okay, so something like this, you grip it and then you pull it apart. Okay, so it records until I mean, what force will it take to fracture these rebars, right? So we have also a stress strain curve. So we have stress, of course, that's tensile, and then we have a strain, and we get a curve something like this. So again, it's almost the same that for low grades we have the higher ductility, but for high grades meaning high strength. So high grades get less. Okay, we'll just write less ductility. Okay, higher ductility. Okay, so why does it matter? Or what's the meaning of this ductility? It just means that you can take more deformation before fracture, or before fracture. All right, so I guess this is the end for this chapter, and in the next video we'll start off our topic on the singly reinforced beam. See you in the next video.